Hi, this is week 36 of AP Physics, and we're going through Unit 10, which deals with mechanical waves and sound. For our lesson agenda, we're looking at the interference and superposition principles, as well as beats. For our lesson objective, students will learn how waves can be constructive and destructive, as well as how beats are found. Let's go ahead and get started. Let's go ahead and start our lesson on interference and superposition. Two wave pulses can interact in such a way as to produce amplitude variations in the resultant wave. When two pulses cross, they travel through each other. They do not bounce off of each other. Where pulses do overlap, the resulting displacement can be determined by adding the displacements of the two pulses. This is called the superposition principle. Let's go ahead and check out a video on two waves colliding with each other. In this video, we're going to see the superposition principle. So waves are going to be generated, and as they move down the medium, you pay attention to their amplitude. Let me pause it there. Now look at their amplitude, their height. Now as they approach each other, they're going to go ahead and go past each other, but while they are in phase, they're going to go ahead and increase the amplitude, so which is the height. So let's go ahead and take a moment to look at that. And there you can see it. It is much higher than the two other waves. So that is the superposition principle. When the waves meet and they are in phase, they're going to go ahead and increase the amplitude of the overall wave. When a wave pulse reflects from a rigid boundary, the pulse is inverted. As you can see in the diagram, you have an incident wave coming in on the top side of the rope here in part A, and notice that the end of the rope is rigid, so it's attached to the wall. Once it goes ahead and bounces off of the wall, it's going to bounce back and it's going to be reflected, but it will be inverted on the bottom side of the rope, as you can see here in D and E. On the other hand, when the wave pulse reflects from a free boundary, the pulse is not inverted. So you see the incident pulse coming in, but you see the rope's attached to a ring that allows it to go up and down. So you see here in picture B, it will go up and down. So when the wave reflects, it will still stay on the top side of the rope as the reflected pulse. Now let's go ahead and take a look at some videos of waves bouncing off of a free end and of a secure end. In this video, we're going to see the behavior of a wave when it reaches the end of the medium and the end is open and able to move freely. So as the wave is generated and moves down the medium, so there you see it, it's above the medium. And since we have a free end, it's going to go ahead and return also above the medium. In this video, we're going to see how a wave is reflected when the end of the medium is fixed, so it's not allowed to move. So when the wave is generated, you'll notice that it's above the medium. That's the incoming wave. But now it's reflected, it will be below the medium. So once they have a fixed end, the wave will return, the reflected wave will return below the medium. Now let's take a look at some definitions. A standing wave is created when an incident wave and a reflective wave meet. If the waves meet in phase, an antinode is created. That's a constructive interference. If the waves meet out of phase, a node is created. That is called destructive interference. Here in this picture, you can see the antinodes pointed by the green arrows and the nodes pointed by the red arrows. The wavelength is represented by the purple arrow. Antinodes are created when waves meet in phase. For example, in the picture on the bottom left corner, we have these two waves here in blue and yellow, and they're going to go ahead and meet in phase. Notice that will create larger displacement from the equilibrium point, so a larger amplitude. On the other hand, nodes are created when waves meet out of phase. So here our blue wave and our yellow wave are out of phase. When one goes up, the other one goes down. They end up canceling each other out, so you get no wave. So that creates a node. Now let's go. In this diagram, we see waves moving down a rope. For the first picture, A, on the top left corner, we have L set as the length of the rope. For picture B on the bottom left corner, it says the fundamental or first harmonic, so N equals 1, and the length is equal to 1/2 of the wavelength. The N and the A, and the N again represent the N for node and the A for antinodes. For the picture C on the top right corner, you see it has a frequency of 2, and the length is equal to the wavelength. Now, for the third harmonic, we have a frequency of 3, n equals 3. We have the length equals 3 over 2 of the wavelength. In this diagram, we're looking at pipes. The pipes on the left are open-ended, but the pipes on the right are closed-ended. Now, how does that affect the movement of sounds? Well, in a first harmonic here, we have the wavelength equals to twice the length of the pipe. And this will be the waves where A, again, is the antinote and the note is in the center. For a second harmonic, we would have 2 waves where the wavelength equals the length of the pipe. For a third harmonic, the wavelength equals 2/3 of the length of the pipe. Now, solving for the frequency, if you have the original F1, the first harmonic, you just multiply it times 2. So for the second harmonic, it'll be double the frequency. If you have for the third harmonic, that it would be triple the original frequency. Now, a couple of terms that you should know. The second harmonics is sometimes referred to as the first overtone. So it is the first tone above the first harmonic. Now let's take a look at the other side where we have the closed pipe. Now notice that the pipe only goes here and the note is at the end where it's closed and goes back. So therefore, the frequency, the wavelength is equal to 4 times the length of the pipe. But for our third harmonic, notice that the closed end does not have a second harmonic. It only goes 1, 3, 5. It goes odds only. It will be 4/3 of the length of the pipe to get our third harmonic. And to get the fifth harmonic, it will be 4/5 of the length of the pipe. Now, this form has changed slightly. Again, if you want the frequency for the third harmonic or the fifth harmonic, it will be the 3 multiplied times the original frequency of the pipe that is closed. All right, so those are the formulas for open-ended and closed-ended for a pipe if you're solving for the frequency of the first, second, or third harmonic.
In example 3, we're asked the following. A pipe is 2.46 meters long. Determine the frequencies of the first 3 harmonics if the pipe is open at both ends. Take 343 meters per second as the speed of sound in air. So it is open, so we're going to go ahead and use this formula to go ahead and figure out the first harmonic. So the fundamental frequency is going to go ahead and be the velocity of the air, 343 meters per second, divided by 2 multiplied times the length of the pipe, 2.46 meters. So for our first harmonic, our fundamental frequency, it's going to go ahead and be 343 divided by 2.46 times 2. Close parentheses equals, should we round it off? Let's go ahead and round it off to 70 hertz. Now, they asked us not just to get the first one, which we did, but also the next 2. So the first 3 harmonics. So for the next part, to get those, it will be this formula. Fn, it's equal to n times the first harmonic. So for our second frequency, it will be 2 times 70, so it'll be 140. And next, for our third, that's going to go ahead and be 3 times the fundamental frequency, which is 70 hertz. So it's going to go ahead and be 210 hertz. And those will be the answers for the first, second, and third harmonics for part A. Now in part B, they are given to us the following, that now the pipe is closed at one end and open on the other. So if it's closed, notice how the formula changes. Instead of being 2 times the length, it's 4 times the length. So now a lot of the numbers are the same, but now we have a 4 here. So it'll look like this. The fundamental frequency is 343 meters per second, and that's going to be 4 times 2.46 meters. Alright, so the answer for that's going to be as follows. So it's going to be 343 divided by 4 times 2.46, close parentheses, 35.8. Let's go ahead and round it off to just 35 hertz. Alright, so that is the fundamental frequency. Next it says, for part B, the 3 lowest possible frequencies. All right, so we got the first one. Now let's get to the next one. So it's F2. Well, actually, no, not F2, because it's closed. So remember, it goes 1, 3, 5, 7, only odds. All right, so the next one will be actually F3. So that will be same formula as before, though 3 multiplies as the fundamental frequency, which is 35 hertz. So that's going to go ahead and be, for F3, 3 times 35 gives me 105 hertz. And the next one after that will be 5 hertz. So again, 1, 3, 5, when it's closed, it's only the odd numbers. So it'll be 5 times 35 hertz. So that's going to go ahead and be 175 hertz. All right, and that takes care of example number 3. In problem 9, we're asked, true or false, the fundamental wavelength of a longer pipe is greater than the fundamental wavelength of a shorter pipe. Yeah, here we have 2 pipes. This is the longer pipe, that's the shorter one. With their fundamental frequencies, yes, absolutely, it is true. The longer pipe will have the longer fundamental wavelength. In problem 10, we're asked the following question. What length pipe opened at both ends has a fundamental frequency of 3.7 times 10 to the 2 hertz? And they asked us, find the first overtone after that. So that's part A. So we're dealing with an open pipe on both ends. So this is going to be our formula. And we're given the frequency. So we want to know what is the length. Notice though that the velocity is not given to us. So whenever the velocity is not given to you, you assume that is the velocity of sound at a temperature of, well, room temperature. So that will be 343 meters per second. So if not given to you, then you assume that we are at room temperature, so therefore it's 343 meters per second. So now that we have this, let's go ahead and move stuff around so we can go ahead and solve for the length. So I'm going to multiply both sides by L and divide by the frequency. So it'll end up looking like this, velocity over 2 times the frequency. So that's going to go ahead and give us the length. That's what they want, find the length, and then after that they're going to want us to find the first overtone. Alright, so now that we have the length, let's go ahead and get 343 meters per second over 2, and the frequency, it is 3.7 times 10 to the 2 hertz. Alright, so therefore the length of the pipe is going to be 343 divided by 2 times 370, close parentheses, equal 0.463 meters. Alright, so that is the length of the pipe. Now it's saying find the first overtone. Alright, so our first overtone, what is an overtone? It is the tone above the fundamental frequency. So in this case, because it's an open pipe, it'll be F2. So that's what we're looking for, F2. Alright, find the first overtone. Alright, so for this one, F2, the formula we're going to go ahead and use is 2 multiplied times the fundamental frequency. Alright, so that's going to go ahead and be 2 multiplied times 370 hertz. So our answer for our first overtone is going to be 370 times 2. It's going to give us 740 hertz. So that's our first overtone. Now, let's take a look at that part B of this problem. It says if one end of the pipe is now closed, what is the new fundamental frequency? Alright, so we have the same length pipe, but now we close one end. So what is our new fundamental frequency? So now we use this formula. So because it's closed now, notice the difference. That's a 2 when it's open, 4 when it's closed. Fundamental frequency, so it'll be 343 meters per second divided by 4 multiplied times the length, which you already found, of 0.463 meters. So our new fundamental frequency is 343 divided by 4 times 0.463, close parentheses, equals 185 hertz. Alright, so that's our new fundamental frequency. And then they also ask, find the first overtone. So is it F2? No, not for a closed pipe. Again, you only use odd numbers, so it's going to go ahead and be F3. So it'll be 3 times the fundamental frequency, and that will give us our answer. So So 185 times 3 gives us 555 hertz. So that'll be our first overtone when it is closed. All right, that takes care of problem number 10. In example 4, we ask the following question. The pictures show a simple apparatus for demonstrating the resonance in a tube. So here we have a tube inserted into water with a tuning fork above it, and you can move the tube up and down to vary the length. Suppose the smallest value for L, for which a peak occurs in the sound intensity, is 9 centimeters. In part A, they ask you, with this measurement, determine the frequency of the tuning fork. All right, so that's going to be our very first order of business. Find the frequency of the tuning fork. So that's part A. Now the frequency, the first fundamental frequency, is going to go ahead and be the velocity that's going to be 4 times the length. All right, now why 4? Well, notice that you have water at one end, so one of the ends is closed. All right, so now we have the formula we need to get the fundamental frequency. So put 1 right here. And given to us is take the speed of sound to be 343 meters per second. Though if not given in the problem, you assume that it's 343. So 343 meters per second is our velocity. Multiply times 4, divided by 4 times the length, which was 9 centimeters. We're going to go ahead and change that from centimeters to meters. All right, so 9 centimeters divided by 100 will give us 0.09 meters. Next, we're going to go ahead and put it into a calculator. It's going to go ahead and give us our fundamental frequency, so that'll be part A. So it'll be 343 divided by 4 times 0.09, close my parentheses, equals, we're going to round it off slightly to 952, let's round it off to 953 hertz. So it's our fundamental frequency. All right, so that is the frequency of their tuning fork. So for part B, it says find the wavelength. All right, so what is the wavelength? So we're going to go ahead and use for part B this formula. Velocity is equal to wavelength times frequency. We got the frequency, and we know the velocity of air, it is 343 meters per second. So we're going to get this formula and use it to find the wavelength. So it's going to be the velocity of air, 343 meters per second, divided by the frequency, which we just got, 953 hertz. So we go ahead and divide those two. 343 divided by 953, and that gives us, we're going to round it up slightly to 0.36 meters. All right, so that is the wavelength of this setup. Now next, find the length giving resonance for the next two air columns that will give us resonance. All right, so for that, we're going to go ahead and we know what the length is, 0.9. So now it's going to be for the next two. So if L1 equals 0.9 meters, then L2 is equal to N times L1. So that's going to be 2 multiplied times 0.09 meters. So it's going to give us 0.18 meters. And L3 is N times L1, which is 3 times 0.09 meters. So that's going to go ahead and give us 0.27 meters. All right, so that will be the wavelength. Here we go. As well as the next two air columns giving us resonance. All right, so that is example 4. In our next problem, problem 11, asks you true or false. The resonant frequency of an air column depends on the length of the column and the speed of sound. All right, so if you look at the formula, yeah, it does depend on the speed of sound and the length as well. So they're in the formula and those affect the frequency. So yeah, that is a true statement. Next, problem number 12 says, an unknown gas is introduced into the aforementioned apparatus using the same tuning fork has this frequency. So it's the same tuning fork with that frequency. All right, and then they ask, and the first resonance occurs when the air column is a length of 5.84 meters. So our length is equal to 5.84 centimeters. That in meters is going to be 0.0584 meters. All right, and we have the frequency, because it's the same tuning fork. All right, so it says find the speed of sound of this gas. Again, they're using an unknown gas, so it's not 384 anymore, it's a different gas. So therefore, we're changing the medium, so it's not it's 343 meters per second. It's not that anymore. It's going to be new medium, therefore new velocity. So we're going to go ahead and solve for that. So it'll be frequency is equal to velocity over, in this case, is close. So this is the same apparatus, so it's going to be 4L. All right, and we now have this length. All right, so now we're going to go ahead and solve for the velocity. So we're going to go ahead and move the 4 and the L over this side. So our formula becomes this: frequency 4 times frequency times length. All right, and that's going to go ahead and give us the velocity of the sound in this new air, in this new medium. So it'll be 4 times the frequency of 953 hertz multiplied times the length, which is 0.0584 meters. And that gives us the following answer. Let's see, 4 times 953 times 0.0584 gives us 223 meters per second. And that is the velocity of sound in this new gas. All right, that takes care of problem number 12.
Next, let's talk about beats. The interference discussed so far have involved superposition of two waves with the same frequencies traveling in opposite directions. But interference can also occur between two waves with different frequencies. So right here in this diagram, we got a blue wave and a green wave. Now, once in a while, they have similar frequencies, and when they meet up, like for example here at time A, they're going to go ahead and have the same frequency, so you get the superposition principle, so you get a louder sound. But here, when they meet out of phase, then you're going to have, they cancel each other out. So it's going to be destructive interference, and therefore you get no sound. So this will create a sound that goes up and down as far as the noise is creating. We're going to go ahead and take a look at a video and listen for that sound. In this video, we're gonna get to hear what beats sound like. So we got two tuning forks that are identical, except that the tuning fork on the left has had a little brace put on it that's gonna change its frequency slightly. And that difference in frequency is gonna go ahead and create beats. So let's go ahead and take a listen to it. Now, the number of beats per second, or the beat frequency, equals the difference in frequencies between the two sources. So that's calculated by frequency equals an absolute value, F2 minus F1, where you have the two frequencies subtracted from each other, and again, it's absolute value. Now let's go ahead and take a look at some examples.
In example 5, we're asked the following question. A certain piano string is supposed to vibrate at a frequency of 400 hertz. To check the frequency, a tuning fork, known to vibrate also at a frequency of 400 hertz, is sounded at the same time the piano key is struck. And the beat frequency is 4 beats per second is heard. Find the possible frequencies of the piano. Alright, so we have a beat of 4 hertz, right? So if the tuning fork is at 400, you want to know what are the possible frequencies for the piano string. Since we have a beat of 4 hertz, therefore it should be either, the piano is either 4 above or 4 below the tuning fork. So for the piano, it's either going to be 400, 4 hertz, or 396 hertz. So those are the two possibilities for the piano. Alright, either 4 above or 4 below the frequency of the tuning fork. That is example 5. Next, in problem 13, they ask you, why aren't beats heard when two different notes are played on a piano? So even if you play two side by side, you don't hear beats. Why is that? Well, in the piano, those two strings, those two notes are far away from each other so that they don't create constructive or destructive interference. So that's why you don't hear beats while playing the piano. In problem 14, it says, the assistant adjusts the tension in the piano, the same piano strings, and a beat of frequency of 2 hertz is heard when the note and the tuning fork are struck at the same time. Find the two possible frequencies. Again, so it's the same piano, but now, so this is our tuning fork, right? Tuning fork. And now we have a beat of 2 hertz. So therefore it will be either, the piano is either at 402 hertz or at 398 hertz. Alright, so that will be for the piano. It's either 2 above or 2 below, since we got beats of 2 hertz or 2 beats per second. In problem 15, you're asked, you are tuning a guitar by comparing the sounds of the string with that of a standard tuning fork. You notice a beat frequency of 5 hertz when both sounds are present. You tighten the guitar string, the beat frequency rises steadily to 8 hertz. To tune the string exactly to the tuning fork, you should A. Continue to tighten, B. Loosen up the strings, C. Give up on the guitar and play the drums instead. Alright, C is not a real option. The answer would be letter B, loosen up the strings. If by tightening the string you got it to go from 5 beats per second to 8 beats per second, ideally you want 0 beats per second, so you want to lower it. So if tighten the string is making the beats increase, therefore you should loosen it up to make them decrease. You want 0 beats per second. Alright, that takes care of this problem. This brings us to the end of our lesson. It is also the end of Unit 10 in AP Physics, which is the last unit in this course. Thank you so much for watching.